Our project is on sentiment and opinion analysis using Twitter data. We look at different classification techniques for sentiment analysis. Sentiment analysis aims to determine the sentiment of a text with respect to the writer. Our goal is to classify the text in a binary fashion, as positive or negative. Sentiment analysis is particularly useful with reviews and when analyzing social media posts. We then wish to extrapolate sentiment onto tweet topics to determine the public opinion of these broad topics. Twitter is a microblogging service that we are using for our training corpus. We got the data from a ThinkNook database in 2012, which contains over 1.5 million classified tweets in CSV format. Linguists suggest that 10% of sentiments are highly debated, so we expect a 10% minimum error. We use 4 different language models and 3 different classification models. For our language models, we use a normal bag of words models for unigrams and bigrams and a TF-IDS discount model, which scores words as higher if they appear more often in the document, but not in the rest of the training corpus, with unigrams and bigrams. Our classification models we explore are naive Bayes, random forest, and support vector machine classifiers.
The first model we consider is a naive Bayes classifier. In an attempt to estimate the Bayes optimal classifier, we make the assumption that features are independent given their label, and this allows us to reduce the search space to a linear number of estimations rather than an exponential. Typically, the naive Bayes estimator has higher error than a discriminative classifier due to the bias introduced by this independence assumption. In cases when the independence assumption is appropriate, though, the naive Bayes classifier can perform very well. The next model we considered was the random forest classifier, which is an ensemble method of multiple decision trees. The decision trees are generated by subsampling the data using a technique called bagging and taking an average of the outputs of the various decision trees. This helps to reduce the variance inherent to the decision trees. In order to train in an efficient amount of time, we were forced to limit the depth of the trees to d to the 1/4, where d is the dimensionality of our feature vectors. In the end, we were able to train the model in 4 to 5 hours, and we had 5 different decision trees in the forest. Support vector machines were our next model that we considered. This model is similar to the linear perceptron, but it better handles noise. It finds a max margin separating hyperplane and incurs a cost for points that are incorrectly classified. It typically performs well in binary classification problems and is not as susceptible to overfitting due to the cost parameter, which allows for some smoothing. In the end, the naive Bayes classifier performed quite well. We see in the chart we have 10 different cross-validation splits with their test accuracies plotted on the y-axis. With bigrams, we were able to achieve a maximum accuracy of about 80%, which was uniformly better than the unigram model. We noticed that naive Bayes trained and tested very quickly, and the performance was quite good. Overall, though, we still think that some bias was introduced by the independence assumption. I'll get into this in the next couple slides. Next, we considered the random forest classifier. We see here that the test accuracy is considerably lower than the naive Bayes classifier. We have a peak of just above 65%, and in some cases the classifier performed even worse than a random coin flip. Although bigrams raw count performed quite well, this classifier on average performed poorly. We think this is due to the fact that we limited the trees to a depth of d to the 1/4 in order to train in a reasonable amount of time and to limit the amount of memory usage. In the end, the decision trees were not able to fit the data to a sufficient extent, so it suffered from underclassification and underfitting. The next model we considered was the support vector machine classifier. This model performed the best, and we see that the bigram model with unweighted counts performed at almost 83%, or just over 83% test accuracy. And at the worst, it was just over 80%, which is very good. We hypothesize that this is because it better handles the interactions between features than the naive Bayes model, which makes the independence assumption. And we substantiate this with the fact that language itself is on a low dimensional manifold. And in fact, the words that we generate are not random with respect to our sentiment. There's a structure to our language and a relationship between the words that we state, so it's not reasonable to assume that they're independent at all. In the end, the SVM was also very efficient during train and test time. The best performing model that we witnessed was the support vector machine using bigrams unweighted. The support vector machine on average performed better than all of the other models, and with random forest performing the worst and naive Bayes performing just below support vector machines.
Overall, we found that our classifiers worked well in most cases, but in other cases, such as capturing many lexical implications, specifically in semantics and pragmatics, our classifiers did not perform as well. Common sense is very hard to teach to a classifier. The classifier can't pick up on sarcasm, jokes, and homographs. Overall, we see that sentiment does not always generalize to opinion.
Now we'll give a brief demo of the trained classifier and our web front end that we developed. We can type in here a query to the Twitter search API, one which we may expect to be positive. For example, happy, we would expect most people would have a positive opinion of it. And we see, as expected, that 97% of the tweets returned are positive, and here we see a list of those tweets. So here is a perfect example of when opinion and sentiment are the same. We expect that people have a positive opinion and a positive sentiment when discussing happiness, or the word happy specifically. In contrast, the word angry, we would hope, or we would expect a negative sentiment, and that is indeed what we see. Most of the tweets that come back have negative sentiment, and then when we generalize this to say negative opinion, it seems reasonable to make that assumption. However, something that we also observed in our usage was that in some cases there is a huge disconnect between the sentiment of a tweet and the opinion of the person speaking. For example, when we search the word rape, we would expect that people have a negative opinion of this term, but our classifier actually detects that there's an overall positive sentiment in the tweets. So does this mean that people have a positive opinion about rape, or that there's a disconnect between sentiment and opinion? And when we read through the tweet examples, or we look more specifically, we see that the discussion surrounding the topic of rape is a lot more complex than just the user's opinion of rape. In fact, they may be, or rather of their sentiment towards rape. They may be discussing current politics or current cases in the media, or even extending support to those who were victim to rape. And these are all aspects of language that are very difficult for a classifier to capture because there are implications based on the links and the pictures and even the words used that simply can't be picked up by any sort of classifier that we've trained. So therefore, we conclude that we've produced a very effective sentiment classifier, but sentiment does not always generalize well to the average opinion of those who are composing tweets.